Alright nerds, so we're going to continue on with our acidic environment, and these are the dot points we're going to cover today. So that might be an indicator that this is going to be a rather large one. So we want to identify natural industrial sources of the two oxides we're going to look at, which are sulfur dioxide and oxides of nitrogen. We want to describe these using equations with where they come from. We want to have a quick look at the evidence. We're going to do that very briefly, and it's going to be there'll be another video for you to watch that'll cover that aspect. And we want to be able to explain the formation and effects of acid rain. But we can have a quick look at it here. This is in 1908. This is the same statue. This is a photo taken in 1908, and this is a photo taken in 1980 or 1988, something like that. And we can see the damage that it's had on the limestone. Now, this is just limestone. This is not a living thing. It's a building, and it's affecting art and such. But it's having can have a fairly serious effect on the environment as well. But that's just one thing there. That's one thing it can do. So we want to be able to explain the sources of acidic oxides in the environment. So both from natural and human or industrial sources. And you want to do it using chemical reactions. You also want to be able to explain the formation of acid rain. Okay, so there's a lot in there. It seems like a little bit, but there is a lot there. Now remember, you need to remember non-metal oxides tend to act like acids in water, that acids create a hydronium ion, and that this will neutralize when reacted with a base to form salt and water. And oxides are chemical compounds caused by something reacted with oxygen. Alright, so here is a source, this is in China, this is a source of sulfur dioxide. So they're burning coal, burning dirty coal, and we can see what it's doing to the environment. This is a recent photo too. We're talking a photo that's only 2 or 3 years old, and this is the sort of effect it can have. So here, this is in America, and they actually cleared up their act a lot, basically, through what was essentially the same as what was called the carbon tax here. They had the sulfur dioxide pricing, sulfur dioxide tax, that worked exactly the same way, and it worked. You can see here that it got rid of these are the older trees which had acid rain, and it was just ripping them apart. But given time, these are the next generation of trees that have come through here, and you can see that they tend to be okay. So what are the oxides that we're looking at? Essentially, the oxides of nitrogen are nitrous oxide, nitric oxide, which is NO, and nitrogen dioxide. And this is what they look like over here. So you've got nitrogen oxide, nitrous oxides there, nitric oxide, and nitrogen dioxide. Then we want to look at sulfur dioxide, which, if we remember from our preliminary course, looks like this. Alright, so where do these come from? Essentially, there are natural sources for both. Now we'll look at the natural sources first. So you've got your geothermal hot springs, you've got your emissions from volcanoes, bushfires, and natural decay of vegetation. Basically, anything that is breaking down biologically will release sulfur. And here's a quick reaction that shows us. So we've got the dihydrogen sulfide plus oxygen. There should be a little arrow in there. Goes to sulfur dioxide and water. Okay. Now, in nature, nitrogen tends to come from lightning and bacteria as a byproduct. Industrial sources, this is where it starts to cause problems. So burning fossil fuels which contain sulfur, like coal and oil, okay, it's in there as a trace element. So we have this reaction which gives us sulfur dioxide. When we're extracting metals from sulfurous ores, like they're there, and this gives us, so we get zinc sulfide to zinc oxide and sulfur dioxide. Alright. Nitrogen oxide, basically indoor domestic appliances, so things that we're cooking with essentially, or heating up gas. That's one place that nitrogen oxides come from, and your cars and motorbikes. So, but here's just a very quick one. So here's what, the volcano sets out ash and sulfur dioxide. The sulfur dioxide reacts in the water, in the air, to make sulfuric acid. Alright, so these are the reactions leading to oxides in the atmosphere. Essentially, if we've got we'll go through these one at a time. Highlighter. So you've got your metal sulfide smelter, alright? So this is one reaction here. Now you've got your zinc sulfate, gets reacted with the oxygen, and it comes up with sulfur dioxide. Oh, sorry, zinc sulfide, not zinc sulfate. And zinc oxide. Cool. if we burn coal, petroleum, and gas with stuff that with sulfur in it or sulfur compounds, this is the reaction we end up with there. You need to know these reactions. Lightning strike. So there are two sources of sulfur dioxide in the atmosphere. The nitrogen ones are a bit different. So we're going to look at two sets of reactions here. So here are two ways to get your nitric oxide in there. So you've got lightning strikes, okay? So the two most common gases in the atmosphere, the lightning comes down with intense heat and electrical energy, and it will break these atoms apart, and then they'll reform to make this one, okay? When I say break these atoms, I mean break these molecules. The high temperature combustion, so again, lots and lots of energy, breaks them apart when there's nitrogen in there to make nitrogen monoxide. Cool. Now, nitrogen monoxide is actually fairly neutral and relatively colorless. Well, it is colorless, but relatively neutral. It reacts with the oxygen in the air to form this bad boy, nitrogen dioxide. So we go from this just in the atmosphere. So as this is released into the atmosphere, it reacts with the leftover oxygen and causes that. And here we have a rough approximation. If you want to give it a quick drawdown, very, very neat. So we want evidence for it. Now, because we're scientists and that's how we roll. So basically, the increase in atmospheric concentrations of these, where do we know? How do we know? What's it evident from? Basically, the formation of acid rain. Now, it wasn't there beforehand. So when we started to Industrial Revolution, we started to pump these things into the air. That's when acid rain tended to start, and it's caused damage over many, many years to things which are stable, like buildings and whatnot. So there's a buildup of atmospheric pollution, which we know has built up, and this contributes to photochemical smog. So essentially, smog doesn't exist. It's kind of colorless until the higher part of the day when it gets the energy from the sun, and then it becomes all smoggy. That's why it's called photochemical smog. So basically, these really lead to health issues, particularly sulfur dioxide and nitrogen dioxide. Now, there's lots of evidence basically for an increase in carbon dioxide over the last 2 centuries. It's here and it's getting higher and higher, and that's bad. There's tons and tons of evidence for it, but the evidence for the other oxides are actually quite hard to get. And the reason is that they're very, very soluble in water, and they're tough to get. Like, they're in smaller amounts, and we basically only have the technology to observe it back as far as 40 years or so. So it is quite tough to tell how, in numerical terms, like if we were to graph it, how much it's risen in the last 40 years. Beyond that time. But there is, like I said, there is the other evidence for it, the secondary evidence, the effects of it, which we can see, and they've been occurring since the Industrial Revolution. So they're soluble in water, so it's tough to compare it with the past. But we know that the acidic oxides have increased dramatically because we know what we're putting into it. Like, we know that we're pumping much, much more of sulfur dioxide into the air than would naturally be there. These gases, however, they tend to be, because they're soluble in water, they get washed out in the rain. So there's not a huge buildup in the atmosphere. They don't tend to, but they don't need to either. They don't need to build up in the same levels that CO2 does. So they start to build up, it rains, they're washed out, and this is one of the reasons it's really hard for us to gather direct evidence as opposed to evidence of the effects. Now, around most major cities, the concentrations are about 0.1 part per million, and this is not super harmful. But if we go to other cities, such as some of the ones in China, it can be much, much higher. So the real concern is when it's at higher than safe levels before rain. Like, that's the problem. It might dissipate over a while and resediment, which we'll see in the next picture. It might resediment as a solid, and we can deal with that. But if it builds up to a really unsafe level before it rains, that's when we have troubles. So here we can see the sulfur dioxide. That would have a 2 in front, and that would have because remember, we don't use fractions for our coefficients, so that'd be a 2, 1, 2, 2, 4, and so forth. Here is essentially what happens with acid rain. It builds up in the clouds, and creates the acid as it, reacts with the water. All right, but let's look at that in a bit more detail. So sulfur dioxide, it reacts with the rain in the atmosphere, and this forms sulfurous acid. Okay. Now, the sulfurous acid reacts with the oxygen, and it's usually catalyzed by air particles. And that's kind of the same as nucleation points. It gives it that bit to react on. So the sulfurous acid reacts with oxygen, which gives us sulfuric acid. Okay, so these are the steps in the reaction. Now, the nitrogen dioxide also reacts with rain, and this makes nitric and nitrous acids. So here we go. So there's your nitric and nitrous acids. So the nitrous acid will react with the oxygen again, being catalyzed, and give you more nitric acid. The difference between nitrous acid and nitric acid and sulfurous acid and sulfuric acid is that they are strong acids. Now, strong actually means something. It doesn't mean concentrated. It means strong acids. It's about how they separate from their hydrogens. So the pH reduces to 3.5 or to 3 to 5, and this is super harmful. And you've seen some examples of it now. It will also have a serious impact on waterways and fish, frogs, etc. All right, so that was a long one. I hope you stuck through to the end and took lots of notes, and we'll see you later.